Okay. Today I will be talking about algorithms for timing analysis. In the last lecture, probably you have gone through some of the terms related to timing analysis like false path, etc. So today we will look more into algorithms part, the approaches how the timing analysis is done. Okay. So you know why timing analysis is required, because you have to find out the clock speed. So for that you need to measure the critical delay, because critical delay determines the clock speed. Okay. Another important concept probably you have gone through is slack estimation. Slack estimation is required to identify which portion of the circuit is critical for timing, and so that you can optimize only on certain portion of the circuit. So, and last is critical path identification. It's very much required. So I'm not going into details of this. Okay, so when we come to timing analysis, so we are given a circuit and we want to determine the critical delay. So that is the main problem. So, so the first input is circuit. So circuit can be in any form. It may be in behavioral form like Verilog. It may be in gate level, some AND or NOT gate, maybe in transistor level. So that is consist of NMOS, PMOS, and resistance, capacitance, etc. So so at the very high level, when we are in Verilog level, so at that point of time we cannot determine the critical delay of the circuit accurately, because we don't know the exact behavior, exact low level behavior of the circuit. So that is the main problem. When we come to gate level, we have better notion of the circuit, how it is going to be implemented. So we have a better notion of the delay. And when we come to the transistor level netlist, we know the exact circuit and we can apply the appropriate vector and determine the critical delay. And actually we can apply a vector and estimate the delay for that. So so transistor level timing analysis is very accurate, but it's very computationally intensive, because you have to solve lot of equations. So it takes lot of time. You cannot handle large circuit. When you come to gate level, you can handle moderately large size circuit, but it's not so accurate compared to transistor level. And at the very high level, RTL level, it's just how many cycles you require. So that can be estimated, but you cannot estimate the exact delay for the circuit. So that is the level of abstraction of the circuit that plays the crucial role in estimating the critical delay accurately. Now comes okay. So today what we will see, we are given a gate level circuit and we want to estimate the critical delay. That is our the main purpose. So given a gate level circuit, fine. So what other information we require? We require the delay models. Delay models means what is the so given a gate, what is the delay of the gate? Delay of the gate can be given of various forms. So I can give the worst case delay. Say the delay is 5 time units. Okay, I can refine the delay models as the rise transition delay is your 5 time units, fall transition delay is your 3 time units. That can be given, and various other combination can be also given. We will come to later after some time. In addition to it, we need to consider the Boolean functionality of the circuit. Why? Suppose I am given an AND gate. If one of the input remains in logic 0, then whatever transition takes place in the other input, that cannot propagate to the output. So that plays a crucial role in determining the critical delay. So we need to consider the Boolean behavior of the logic circuits. And finally, the types of circuit, that means it's combinational or sequential. For sequential, you have to consider the combinational portion of the sequential circuit, and in combinational circuit we will consider all combination of primary inputs and outputs. So that is the main modeling issue for timing analysis. So in this slide I am showing you various components of delay. So first thing is slope delay. Here you see this is the when a transition takes place at node B, this transition can be of this form or can be of sorry can be of this form. So this transition, the slope of the transition can play a crucial role. So this is called the slope delay. Here, this is an intrinsic delay of the gate that is inherent within the gate, and this connect delay is C to D, that is the to propagate a transition from C to D, that is the connect delay, and the transition delay is the it, this is after suppose there is a transition here. So this transition takes place within the various transition takes place within the gates. Finally the output has to stabilize, that is called the transition delay. After all switching that happens within the circuit, after that the output will be stabilized, so that is called the transition delay. Okay. So this is the various components. So even the delay also depends on the loading of the output, loading at the input. The capacitance you have to also consider to get an accurate model. So in case of static timing analysis, often what happen is that the slope delay that can be assume a fixed value and can be replaced here by a fixed delay sized buffer. So I can, for algorithmic purpose, I can assume there is a buffer of that amount of delay. Okay. Similarly for the others can be also consider. So now we are given a circuit, we want to estimate the critical delay. That's our main motivation. So this is a circuit, pure combination circuit. There is no loop that you can see. The numerals within the gate represent the worst case delay. Okay, 3, 2, 1, 4, all those values. So how can we determine the critical delay of this circuit? So the first observation is that we can modify this circuit to a graph. The graph will be acyclic and directed. Is that okay with you? You know the graph data structure. Okay. So we want, so how you can convert this to a graph? So each primary input I'll be considered as a node, each gate will be considered as a node, and the output will be considered as a node. The connectivity will be obtained from the circuits. So see the graph. So this is the node for gate G1. This is the node for I1 input. All these are inputs. These G are the G are the gates. These are the outputs O. In addition, I have added two nodes, that is S and T. The S is the source node, T is the target node. Okay. So this is just dummy node, and I have added the edges to this one. So just to ensure that I have a single source and single target. So, and what I have done here, I have written 3 2 along the gate node that represent the delay of the corresponding node that is obtained from the circuit. Okay. Now we want to perform a topological analysis. Topological analysis is that it determines the it finds out the longest path in a given graph. It doesn't consider the Boolean nature of the circuit. So for that we assume the source node has 0 delay, input has 0 delay, because we have not written any delay values here. The blue, the text on blue is represent the gate delay, that we understand. So now we start with the delay calculation. Since this is the source node is 0 delay and input node has 0 delay, so the delay for these nodes will be your 0. Fine. Now comes the actual part. I can estimate the delay of a node only when its delay of the fan-in nodes has been computed. What I mean is that suppose I want to compute the delay at Z5, I cannot compute the delay of Z5 immediately because I don't know the delay of Z1 or Z3. So what we have to do? We have to compute first G1. Okay. So Z1, I can estimate the delay of Z1 because I know the delay of I1 and I2. So its delay will be the maximum of this or this plus node delay. So it's 3. Fine, everybody. Okay. Similarly for G2 we can compute. It's 2. Okay. For G3 it will be 4 because the Z2 has delay 2 and Z3 has delay 2, so it's 4. Max of this and this, so it's 2. Max of 4 and 2, so it will come to 4. Okay. Similarly, we can estimate the delay for the other nodes. I'm not going into the details. Just see, it's okay. Everybody. 6. Finally, it will be 8 and 6, and finally I will take the maximum. So it will be 8. So this is the topological delay. Okay. What we have done, we have not considered the Boolean nature of the circuit. Okay. Now we will consider the Boolean nature of the circuit and try to find out the delay. So suppose this is the given circuit and the delay model has been improved here. The delay model here is the rise delay slash fall delay. That is the notation here. Okay. So for the first, for the first gate, it's 2 is the rise delay, 1 is the fall delay. Okay. So any transition here, if there is a rise transition, so since it's a gate is NAND gate, so output will be a fall. So in that case, is if it's at time t equal to 0, then output will be at t equal to 1, because we have to consider the fall delay. So if I perform topological analysis on this circuit, can you tell me what will be the delay? Just one thing I would like to add here. In topological analysis, it assumes the worst case delay. So if say this is 2 and 1, so in topological analysis, the delay will be considered as 2. So can you tell me what will be the delay if we perform topological analysis? This is a simple one to compute. You have to take the maximum for all the gates, and then you have to find out the longest path. So this is very easy. 4 in the first level, it's 4. There are 2 gates 4. Here is 1, 5. If I take this path, 5 plus 3 is 8. 8 plus 3 is 11. 11. So that's 11. Okay. Now we are going to consider the Boolean nature of the circuit and find out the delay. So for the rise transition, the delay will, for any rise transition in this input, the delay output will be of negative nature. So we have to consider 1 here for rise transition, because there will be a fall transition at the output. So the delay value will look like this. For rise transition, it's 1. For fall transition, it's 2. Because if there is a fall transition here, so output will be a rise. Okay. Similarly, for the other gates in the first level. Okay, clear? So can you tell me what will be the delay for node E? For node E, you have to consider only these two values, 2/4 and 1/3. 4 plus 1 is 5. So okay. Okay. So what about node F? Three plus 2 and 3. So that the fall, so there will be rise. It's 6, and for 5 it will be fall. So 7. Clear? For G it will also come 6/7. So now tell me what will be the delay for node Y. Got the point? 8/9, because 6 is the rise transition here, so it has to be considered fall, so that's 9, and for the other one it will be 8 and 9. So suppose we are given this circuit. So what will be the critical delay for this circuit now? So maximum delay, it's 9. So if you analyze topologically, you will get 11. So if you take the Boolean nature of the circuit, you will get 9. So you can see that there is a improvement on the delay estimation. In the topological analysis, always estimate the upper bound. Okay, so if you want to find out the accurate delay, you have to consider the Boolean nature of the circuit. That's here. Okay. So there is another concept called false path. Probably you have learned in the last lecture. This is a path which cannot be sensitized using any inputs at the primary given at the primary inputs. Okay. Here I have shown an example that path X, A, B, C, D is a false path. The path drawn in red. So you can realize that one. So suppose I want to propagate a transition from X to D through the path A, B, C. For that I have to set the value Y. I have to set the value 1 at node Y. Fine. For Z, I have to value set 1 once again. Here I have to set value 1 once again. For that, what I have to do, this is has to be 1, so this has to be 0, so one of the line has to be 0. So that's the conflict. So that's why this is X ABCD is a false path. There is another example on false path. Probably it's very easy to see. So what will be the critical delay for this? 10-20 of the delays. No delays on the marks. So it's 30. Actually, there are two paths that can be activated. So from this red and the blue one. So we cannot have a path that propagates through 20-20 delay unit. So no path with delay 40. So this is its basic basic conception of false path. Now we go to the algorithms part of it. So how we can find the false path with proper algorithm. Before that, we introduce two notation. First, controlling value and non-controlling value. Controlling value is a value at one of the inputs of the gate that determines the value at the output irrespective of the other inputs. So for example, suppose given a AND gate, okay, suppose this line has the logic value 0, so output will be 0 always irrespective of the value in this input line. Maybe it's 1, maybe it's 0, so it doesn't matter. So 0 is called the controlling value for AND gate. Okay. Similarly, if we consider OR gate, so what will be the controlling value? It's 1. Okay. The non-controlling value is the complement of controlling value. So that means that value cannot determine itself the value at the output. For example, in AND gate, if this line is 1, I cannot tell what will be the output. So I have to consider the other input. So this is two of the main conception that will be required to analyze the circuit. So this is the floating mode time analysis that I have written here is one of the most popularly known approaches in timing analysis, and widely you can find a lot of papers on that in the literature. So these 2 points says that, okay, just before that I just want to give one example. Suppose this is an AND gate, okay, so suppose this line stabilize to logic 0 at this time point, okay, suppose this line also stabilize to 0 at this point, okay. So can you tell me which waveform will determine the delay, critical delay here? So only considering only these two waveform. the first, this waveform will determine the delay because this is the uh, earliest event, first thing. And one important thing, this is the controlling value, but it goes to controlling value, so it determines the output. In other case, suppose this waveform is goes to logic 1 and this goes to 0. This can be also here also for this and this. Whatever may be the case, it will be determined by this waveform. What I mean is that I just forgot to mention one thing. In this delay analysis, so it is considered that initially it was in unknown state, is stabilized to known state. That is the main thing. So whenever I give an waveform, it means initially it's in unknown state and it stabilizes at that point of time. So if this be the case, so I can exactly tell the delay will be determined by this one for this case. Okay. So the point here is that the delay is determined by the earliest controlling input. That is my point, because this goes to the controlling value. In this example, this also goes to the controlling value, but the the input that stabilize earlier, that determines the delay. So it is the earliest controlling input that determines the delay. So now the other case, when it stabilizes to non-controlling value, what happens? You can consider the example also. So this stabilizes to non-controlling value. Okay. So suppose this stabilizes to controlling value, so it will be determined by this. Okay. And for this case has been considered in the other side. In this case also, what happens? Both stabilized to non-controlling value. So this can stabilize here, or this can stabilize after some time. So this is the time point. So you can see that if this stabilize here, so this will determine the delay, because this is the last value, because I don't know what is the value earlier. So after this time I can tell what will be the value at the output. Similarly, if we consider this waveform and this will determine the output. So the observation here is the latest non-controlling value will determine the output. So these 2 points are written here. Okay. Fine. Now we will go through one example using this approach, earliest controlling input and latest non-controlling value with this. So here I will be representing a pair with logic value and time. For that, see, in this case, just I specify that the node A stabilized to 0 at t time equal to 0. First one is logic value, second one is time. Similarly, node B stabilized to 1 and time t equal to 0. Now we want to compute the delay. Basically, this is called timing simulation, because I have the input vector, I'm just simulating over the circuit. So this simulation using this approach. So node C will have the value logic 1 after time t equal to 2. Fine. Similarly for node E, for node G it will be 1 4. Why? Because C is 1, there is the controlling value, and this node D will have 0 non-controlling, so it is okay. Fine. So what will be for H? Fine, everybody is getting? So now tell me what will be the value for Z? This is 0 because there is the controlling, so that will be that determines the output. So it is 0 4. Okay. Now I'm going to introduce few terms, and then we will see one example and the proper methodology how to compute the delay and find out the false path proper approach. Basically, in this example, we have shown simulation. Given the input vector, I can determine the delay. Now our approach will be, given a path, I have to find a vector that sensitize the path. Okay. So for that, I am introducing few notations. So this is SC is stable controlling value. That means this set of input vectors for which node F has controlling value. So if I write this mathematically, so it will look like something. Set of vectors, fine, for which the node F has the controlling value, that means stable value. So I am using stable value of node F for the vector V, that is the controlling value of the gate, say G. Okay, suppose this is a gate Z and there is a node F here. Okay, is it okay? Now I am defining the non-controlling value of stable non-controlling value. Stable non-controlling value of node F, that is set of vectors for which stable value of node F is non-controlling value of the gate. Everybody is okay? Just I am defining these terms here mathematically. Now I will be defining earliest controlling input or earliest controlling time, whatever you say. So this tells the set of vectors for which node F can stabilize at earliest at time t. So that means it can at most stabilize t or later. So the set of vectors for which stable value of node F comma V is value controlling value of the gate Z and is the earliest time. So stable time of node F V, node F corresponding to on application of vector V is greater or equal to t. So it can stabilize earliest by t. So there is the third term. Now I'm defining the fourth term. So this tells the set of input vectors for which node F will be stabilized latest by time t. So set of input vectors for which stable value of node V is non-controlling value and it stabilizes before time t. So stable time everybody is clear with this? Okay. So now we want to determine the delay for the okay, let me put it in this way. Suppose I'm given a path and I want to determine the vector for which the path can be using applying which the path can be sensitized. Okay, so suppose this is a part of the path and somebody has provided me the input vector for which I can sensitize from a primary input to node Fi, say. So 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 assume that vector is xfi rather. Okay, somebody has provided me that input vector that sensitizes from primary input to node Fi. Okay, now I want to determine the set of input vectors for which we can sensitize this path from Fi to Fi plus 1. Okay, that's our goal. So there are two cases. First thing is if I can stabilize to controlling value, if I can stabilize to non-controlling value. Okay. Suppose if I stabilize to non-controlling value. Okay. So that is the set of this input vector. Fine. And for non-controlling, it will be your fine. So for this case, if this stabilize to controlling value, so in the other input, so that is called side input. Say side input can have non-controlling value, can have controlling value. If it has non-controlling value, then we don't bother because controlling value will determine the delay. So we can take the set of input vector for which it stabilized to non-controlling value. So that is given by SNC SI. Fine. Okay. Sub the other case that remains is it stabilized to controlling value. So that means it has to stabilize later than node A5. So that is the set of input that is given by ECT. Okay. And one more thing, suppose this delay is called say tau here. Okay. So that means it has to ECT. So for this case, this uh, for this case, the delay will be determined by the node Fi. Okay. The other case, when the node Fi stabilized to non-controlling value, in that case, what only one possibility left is other node has to be stabilized to non-controlling value and has to be later than node Fi. So that remains LNCT. Oh, sorry, earlier. It has to be earlier. So we have two sets. Now we want to combine these two to determine the exact vector for which I can sensitize from Fi to Fi plus 1. That is the combination of these two. So if I write the full expression, it will look like this. Is that okay? This is basically the set of input vectors ANDed with these input vectors plus means that's the logical OR this input vectors and this input vectors. So this determines to sensitize from Fi to Fi plus 1. So if somebody has given me the input vector to sensitize from a primary input to Fi, so if I just do if I take a logical AND with this, so that will give me from primary input to Fi plus 1 along that path. So somebody has to provide me this one. So this is looks like kind of mathematical induction. So we can propagate in the same way. So basically we need to determine the input vectors for the primary inputs. So that will be given as x. See, any primary input can be sensitized by any vector, maybe 0 or 1, whatever you can say. You can set any value there. Okay. Till now, if you have any doubts or if you have any queries, no. Okay. Now I will take an example to show this one. Okay. say the delay for this gate is 4, 3, 2, 1. Okay. I want to sensitize the path B, D, E, F. That is our path of interest. Sorry, B, D, E, Y. I'm sorry. Okay. So we will start with uh, we'll be basically considering all these terms that we have shown earlier. So to start with, x, b, this is the input vectors for which b can be sensitized. It means the a can have any values. I don't bother about a. For b, it can be 0 or 1 that can sensitize b. That's the primary input. Okay. Now I have to consider node D. Since this is a single input gate, any transition at the input can propagate to the output. So from node B to node D, it will be same. Is that okay? Now comes the actual part. I now I want to sensitize from D to E. Okay. So for that, what I have to calculate? You remember the uh, equations that I wrote earlier. Okay. So I need to compute stable value at node D, that is this value. Then I have to compute non-controlling value of side input, that is C. Earliest controlling input for side input. So what will be the tau here? Tau is 3 here, so we have to compare with 3, so it will be 3 because the delay along this path is 3. There is a NOT gate with 3 time unit. Then we have to compute the non-controlling value for the on input, that is, and finally that we have to compute. Okay. Yes. Since I'm considering the path BD till now, okay, so the delay along this path is 3. It's fine. Here I am computing, I need to find out for the set of input vectors for which these nodes stabilize later than t equal to 3, because at later point of time I will be considering this path. This node stabilize to t equal to 3. Sure. Okay. So if it's 3, then if the other input has to stabilize to controlling value, then it has to be later. So for that I have to consider 3. Okay. Since D is stabilized to t equal to 3, so if the node C has to stabilize in controlling value, then it has to be later. So earliest controlling means it can stabilize at most at earliest by t equal to 3. XB is the set of input vectors to sensitize node B. For that, these two represent the value of A and value of B. The node A can have any values to sensitize B. B can be sensitized by applying 0 or 1. So I'm just writing in 0, instead of writing 0 and 1 explicitly, writing X. So I can sensitize B using any combination of values. Okay. XD can be the same because any transition here will propagate to node D because there's a NOT gate, no other input that is controlling. Okay. Any more question? So, so can you tell me what will be the value for controlling value of node D? So if it has to be controlling value, that means it has to be 0. That means B has to be 1. Okay. And I don't bother about A because A has no control over D. So it can be anything. Okay. So what about the next one? Controlling value for non-controlling value for C. Non-controlling value of C, that means it has to be 1. That means at most one has to, at least one has to be 1 among the A and B. Oh yes, sorry. This is non-controlling, so it has to be 1. So both has to be 1. Fine. The next one, earliest controlling for node C and after t equal to 3, but the delay is 4 here. So all values, all values means it's controlling. So one of them has to be 0. Okay. So that is I'm writing 1x and x1 because this actually combines 3 input vector 1 0 1 1 and 0 1. Sorry. Yes, yes. Okay. So
After delay being less than 3, then you would have got
5.
5.
So whatever the next non-controlling value of node D, because
X comma 0.
x comma 0. Fine. So last one, this is the non-controlling value for node C and has to be stabilized earlier than 3. It's impossible. So it's 5. Fine. Now you can put these values into this equation and get the final expression for the input vector.
So how do we add and multiply?
Yes, I'm coming. So first thing is that uh, xd is given by x and x. So I'm writing the full expression. Then this expression, so this is x comma 1 Sn Si, that means this one plus 0x x0 then non-controlling value for on input, so it's, and then it's 5. Okay. So now we have to compute this one. So how can we do this? First one will remain till now same. So this set of input vectors tells that I have all the input vectors 0 1 1 0 0 0 and 1 1, the whole set. So it is ANDed with x and x1, so it will be your x1. Fine. This is ANDed with 5, so it will be 0, null set basically. So when you combine these two, it will be your x1. Fine. So can you do the next level? Or yes? Huh? Last step. See here, this is, there is a logical AND because I'm, this term basically corresponds to controlling value, this whole term corresponding to this, okay, and this term for this, and the phi is for this. I'm just replacing this value. So now I'm considering this one. This is the set of input vectors. There is a logical OR here. So here I have 0 1 1 0 and 0 0 plus 1 1. That means I have the whole set of vectors possible. It is ANDed with x1. So the second input has to be 1. So I am writing x1. For the next one, it will be 5. Now this x1 and xx, that is logically ANDed. So what will I get? X and 1.
So if x is 0, so say xt was initially 0 comma 0, so output will also be 0 0. But say r output x1 should be xx.
Xx logically ANDed with x1. That means the second input has to be 1. This xx comprises of 4 input vectors, and this comprises of only 2 input vectors, for which second input is 1. I am taking the intersection of these two, so that means it x1. This is logical AND, that is clear. Logical AND means I have to consider the intersection. So you can do the next level. So I'm not going into the details of the next level, okay, so you can do that your own. And till now, if you have any question, you can ask me. Otherwise, I have almost finished. So there is nothing more left. This is a just basic example. This is called the floating mode timing analysis. And if you go through the papers on timing analysis, you will find there is various other approaches also. That is an abstract version of this one. Sometimes they relax some of the conditions, and then they obtain various conditions, like that is called Brandt-Eigner static sensitization. There are a lot of terms that you can see. And other approaches, one thing I would like to mention here, that is called transition mode delay analysis. Transition mode delay analysis is more like a timing simulation, where I have given the input vector, and I just propagate those input vectors through the circuit and find the critical delay. So the problem there is I have to consider all possible combination at the input. So for n inputs, I need to consider 2 to the power n input. So that is very huge. The advantage here is that I am not considering inputs, all the inputs explicitly. I can propagate some Boolean condition like this, so I can obtain the exact sensitization criteria. The one problem here is that this approach is we have to iterate over all the paths, because which path has been sensitized that we don't know. So one approaches can be like that. First we sort all the paths topologically, then consider one by one from starting with the max delay. That can be one of the approaches. So there are various other approaches to consider, like your crosstalk and all those new terms that you have learned in the last class probably. So for that you have to go through the papers on various research papers and just learn yourself. The two things that I have considered here, for reference, the timing. There's a book with title Timing. It starts with from transistor level, RC level to go to sequential circuit gate level. This book is available online in Springer website. You can download the PDF files there. And then the next algorithm that I have told for floating mode, it's from this paper. So that's all.